Okay.
We need a full screen. Yeah.
Okay. Okay. Good morning, everyone. Today I will be presenting this paper. It's called nanometer towards accurate latency prediction of deep learning model inference on the diverse edge devices. So this is the outline of my full presentation. So currently, deep neural networks is widely used in different mobile applications. To name a few, like on-device video analytics, face recognition, and AR and VR. So there is a wide variety of uses in DN networks. And what would we need for a good DN model designs on all these different devices? The most intuition thought is that we need to have high accuracy. Because if we don't have a good accuracy, the task itself is not efficient enough. Also, we need high efficiency as well. And that refers to low inference latency here. That means your operation has more reduced time and it doesn't take that much effort in terms of time consumption. So the approach for this is to use compression model and neural architecture search, these two basic methods, to make sure that the latency can be lowered. So these are the two pictures showing that how compression model and neural architecture search works. So one thing we need to know is that we have to obtain the information of latency, or else all those methods won't work. Now, currently, the issues for measuring latency alone is that it takes a large, immense engineering effort. What does that even mean? It means that given that have so much diverse edge devices, such as CPU, AI accelerators, and a lot of different devices that needs. And also the different inference frameworks, such as TF-Lite, OpenVINO. So all those can be different among different mobile devices. And all these differences makes measuring latency a lot more inconsistent. So these are all the different kinds of edge devices and inference frameworks. You can see just from this graph, there are so many of them. And it's going to get larger and larger in the future. Another problem for measuring latency is that it is extremely time consuming to measure a large number of models in NAS tasks. For example, we'll take one example here. The proximity listeners, they explore for around 0.3 millions of models in just one round of search. So this can take a lot of time to just do for those models with very large capacities. So measuring latency is not a good approach. So the better one is actually to predict the latency prediction. Here we have 3 types of methods, and I'll go through them one by one. So the first one is flop space method. So basically, you just get the information of floating point operations per second. And the problem with this prediction is that it's not really a direct metric of inference latency. It's not intuitive enough, and it doesn't say too much of latency. The second one is the operator level method. You sum up all the latencies of all operators. In this case, operators can mean like a add function or a multiply or convolution and so on, and batch normalization. All these can count as operator level operators. So in the model, there are different kinds and multiple kinds of operators. However, some of the latencies of all operators doesn't actually lead to the true latency of the model. Why? Because they are not considering the latency of the model graph optimization. The model graph is not optimized. We'll take a graph here. We'll take a picture here. For example, say there's operation 1, operation 2. Those two add up doesn't really equal to the same latency as operation 1 through operation 2. So the model latency doesn't equal to the sum of all the operator latencies in the model. And lastly, we have model graph level method, which captures the model graph optimization. So it solves the problem of the previous one. But that is another issue, that since it depends on tested model structure, it may not work on unseen graph models. It may work on the models that we are familiar before, but if today we are introduced a new and unseen model, you might have a hard time to actually predict the latency accurately. So all those three approaches have their own setbacks. So in the next one, we will be introducing this NN meter. The purpose of this is to accurately predict the latency of arbitrary DNN models on diverse edge devices. Keep in mind that here, diverse edge devices is actually big, because that means you can have work on different kinds of devices or governors. So what's the key idea behind this NN meter? We divide a whole model inference into multiple kernels to conduct a kernel level prediction. So in the previous slide, in the previous page, we talked about operate level prediction. We talked about model graph level prediction. Now we introduce the kernel level prediction. So here's a full process of how this kernel level prediction works. And the definition of a kernel is the basic scheduling and education unit. For example, we take as a GPU kernel. That is one of the examples. So the model latency is the sum of all kernels, because that is our approach to this, that we want to make sure that those kernels are sequential and they can, all these latency adds up, they will equal to the sum, and they equal to the full model latency. And this is our goal, and this is pretty much the whole purpose of this NN meter. And what are the challenges we need to face in this new method? Before that, we'll be talking about the benefits of kernel level prediction. So first, it captures the diverse runtime optimizations that reduce the latency. So you have all those different kinds of hardware runtime optimizations, such as GPU, you got CPU, you got VPU, you have all different kinds, and you want to find the best one that can reduce the latency. That is one of the benefits of this kernel level prediction. And also, they are able to predict unseen model graphs. So if someday a new model is introduced, we can still use this nanometer to get a very pretty accurate latency prediction. So here is another process telling that you put a model, you process it in a nanometer, and it will output a inference latency, which is the time consumption, and you pack it up with the optimizations with all those different hardware optimizations, and then you can achieve your goal as to reduce latency and to predict new models. So now we've been talking about the challenge of this nanometer, like how do we actually achieve such a design? First is how to split a model into proper set of kernels. So we talk about this is better than operator and graph, but how do we actually find the best proper set of kernels? Because since executed kernels are varying on different devices, like for example, the convolution can be included in a CPU, but might not be included in the GPU and VPU sides. So all those kernels, they are not really consistent when it comes to different devices. On the other hand, many inference frameworks are not open source. So if it doesn't tell us what it is, how do we actually do the process of splitting the model? And first, we will talk about the solution and the technique to this such challenge. Is the automatic kernel detection. We apply fusion rules for test cases. So we have a test case, and we will go through the fusion rules, and which we will be talking about later. Then we use the kernel search by the fusion rules. And this is the overall thought process of this. We input the model, we have some test cases, and we put in fusion rules. We do the kernel search in the model. So what exactly are those? First, we talk about fusion rules. It's a set of test cases. So these are for example, I'll just take two operators here. So this test case, there are two operators, operation 1 and operation 2. And the TOP1, TOP2 here represents the time of the operator. So you can say it's just a latency of the operator. With these two operators, we can obtain 3 latencies. Keep in mind that's every 2 operators. So we obtain the 3 latencies. What are the 3 latencies? It is indicated already, the first 2, which is operation TOP1 and TOP2, and the third one, which is the fuse one of TOP1 and 2. You might say that it's not really, you can't be sure that TOP1, TOP2 is worse than the fusion of the 2. So you need to compare those 3 latencies in a formula. So these 2 operators can be fusible if the TOP1, TOP2 minus the T of OP1, OP2 is larger than a specific amount of them. And this alpha is, you can determine the value depending on how you want to use, how you want your model and how your fusion you want it to be. So if it's fusible, we can make the operation into a new one.
Huai-an, before you go further,
yeah,
for the operator latency, because it's a little bit out of our areas, right? So okay. How exactly you measure this? the operation latency.
Okay, so operation latency is that it's basically just the a time you take to do this operator, because you have to in order to calculate, you needed some time to actually do that kind of work. So those you can just think it as the time consumption of those operators.
Okay,
If that makes it.
let me change the question in another way. Okay.
Okay.
Do you have a software library, or do you have a specific instrument to measure this kind of operation latency?
We can measure it the operation latency just by looking each individual one. Yes, and there.
Yeah, I believe the operation latency is kind of in the scale of millisecond or something, right? So
Yes.
Is there any specific tools or software library, whatever?
Okay.
Did this paper mention that?
Okay, I think they didn't really mention about how to get those kind of informations, because they pretty much assume that we have the knowledge of those the basic operators.
But we don't, right? We don't. I mean, probably for computer architecture people, they know, but we don't, right? So we would like to know, if I want to measure operation one, for example, how can I do that? Then if I measure the second case, say it's operation one, right arrow to operation two, for that kind of a combined one, how can I measure it, right? So do you have any background knowledge idea how exactly they do that? If no, you just say no. If yes, you just go ahead and answer the question.
Oh, okay. Yeah, so I'm not really sure how they found all these operation.
Okay. Yeah.
Yes.
You try to Google search or whatever,
Okay.
the words.
All right.
Exactly the matter. Okay. Yeah, please move on.
Okay. Thank you. Okay, so this is the introduction of fusion rules. And the next one is the kernel search by fusion rules. So this is through a DFS algorithm. So say there's a model and they have tons of operators. And we go through each two of them. If two operators are fusible, we have to verify that by the fusion rules, and then we can create a new operator. And then this process will continue and until all the operators are no longer fusible and they have reached you can say a optimized kernel state. So then we can output a set of all the constituent kernels. So we input a model, we look into all the operators in the model, and we fuse those operators to new sets of kernels. That is the process of this whole kernel search. So we take an example of this ResNet 18. Of course, this is the subset of a part of the ResNet. So we can see that this is a part of the ResNet 18 model. And you can see that there's Maxport, there's convolution, there's batch normalization. And what they do is that they fuse the convolution BN ReLU into a new kernel, and as well as the below one, which is convolution 2 BN add and ReLU. So that's how the whole fusion works. And this is the output of this ResNet 18 of all the CPU, GPU, VPU, and the numbers of such kernels. And that is how they do the automatic kernel fusion. So now we have detected all, we have found all the kernels. What is the next challenge here? Large sample space cost. So we'll take example of this convolution, this kernel, which is convolution BN ReLU, and this is pretty much the case for most models, that this type of kernel has the most latency distribution. So if we try to sample this space, we get a very large sample cost. We take a look at this to indicate how big of this. So H is the height, W is the width. We have kernel size, we have stride, we have channel number, we have channel output. And all these, if we take it into a calculation, it will result in a very large configurations. So we need to solve this problem. Also, another challenge for this is that the nonlinear latency pattern. Random sampling misses hardware crucial data. What does that even mean? We'll take this as an example. The orange ones are the ground truth of those latency points, and the black ones are the random sampling. So you can see CPU is not that much of a problem because it's linear. But if you take a look at GPU and VPU, you can see that their latency, they progress in a like a stair. So if we use random sampling in this, we might miss some hardware crucial data. As for GPU, you can see that it misses on some of the orange parts of the graph, which is not what we want to see in a sampling. So what is the solution to such a of this problem? Is that we use the adaptive data sampling. We first apply the prior possibility distribution. What is it used? Is to sample the configurations that are likely to be considered. And then we run the regression model. And here we take the example of random forest, and which is the model they use in this paper as well. Then we use the fine-grained channel number sampling for data with large prediction errors. So in the previous, we talked about some of those predictions might be neglected. Now we focus on sampling the data around the data with large prediction error, so that we can make sure we don't miss on any of those crucial data. So this is the full process of this adaptive data sampling. We input the kernels, and then we do the prior possibility distribution. We can sample out those configurations that are more likely in the model, and then we can run the regression model, and when we get data with large errors, we run the fine-grained data sampler, and then we return the data and measure frequency back into the regression model. And this cycle is continued until we reach a accuracy that the user demands. And then we can output the final outcome. So here is a full implementation and how this whole process works. First, we have a set of models. We run the kernel detection, as we mentioned before. Then we can find the best and the most proper way of the kernel sets. And with the new fine kernels, we again run the adaptive data sampling. With the process we just told, the the below is the ML predictors, and the above is the model regression that we talked about previously. With all the sum of those kernels, we can get all the latency of those kernels and add it up to represent the model latency. Since those kernels are sequential, it is no doubt that the sum of them is the exact of the model latency. And here, to continue on, we have 3 edge devices, and we have kernels detected in this benchmark data sets, which is 22 CPU, 26 GPU, and 22 VPU. And the kernel latency predictors, here they use the random forest model, and we will be showing those. First, the 3 edge devices they use, they individually represent the CPU, the GPU, and the VPU. And devices are processor and framework. They are indicated here in this figure. And those are the main, the figures on the right are the main kernel predictors. So we can see there are a lot of them. There are exactly some 1, 2, 3, 4. There are exactly 11 of them, and all those they represent the kernels they found, and divide to analyze. They put it in CPU, GPU, and VPU, and RMSE represents for root mean square error, and the right one is the accuracy. So these are the kernels they found after the process. And these are the benchmark data sets they claimed from there. These are all the model variants. And you can see there are 12 of them. They have shown the average flops. They have shown the latency of those. And with those benchmark data sets, they just created the kernel predictors from the graph. And the comparison baselines. Here are the comparison they are trying to do. First is the flops we just mentioned in the previous latency prediction, flops and plus MAC. So all those 2 are the more seen and widely used latency predictors. And BRP NAS is the one that has been used in the NAS and predictor. So these 3 are the comparison we will be using alongside with the NN meter. So will be 4.
Minor suggestion here. Could you go previous page?
Okay. Yes.
Again, because we're not in this area, right? So it will be good if you can show the full name. For example, the MAC, in wireless networking and in security, it means different things. In security, it means authentication code, right? But in networking, it means MAC layer. So I believe here in the hardware, it has different meaning as well. I'm not sure, but it will be good if you can show the full name of there. Okay. Except the widely accepted knowledge like FL for fair learning, stuff like that. You don't need to show full name. Otherwise, I think it will be good. You can show the full name.
Okay.
All right.
All right. Thank you. Okay. So yeah, I'll continue. So here are the results, and first we will see the performance on unseen model graphs. That means there are new models that we have not yet to know the content of it, and then we can show the results. So on average, NN meter achieves 89.2% accuracy. So it's significantly better than flops plus MAC, and BRP NAS of the 3 on the 3 devices. And here is a graph showing that how all it works. So the orange one is the accuracy of NN meter. You can see it pretty much wins basically every single case. The only one that is kind of close is the VGGS in the CPU. So overall, the NN meter has a brilliant performance in terms of accuracy prediction in new models. Next, we'll look at the kernel level prediction versus the operator level prediction. So how exactly is this better? How much is it better than the operator? In the left and in the right, there are different different ranges for accuracy, but you can see that the black one is the kernel level and the operator level is the gray one. You can see that in each cases, again, kernel level prediction is a much better prediction of those latencies. Keep in mind that all those predictions are based on how accurate latency is. And next is the adaptive sampling versus random data sampling. We talked about random data sampling has some issues with missing the crucial data. So here we can see random sampling, adaptive sampling, and again, adaptive sampling is much better than the random sampling, with accuracy 71, 75, 54 in CPU, GPU, VPU. And all those done, we also basically cover the most of the results of NN meter and how it is beneficial to almost every case. But we might think that how's the time consumption to actually finding all the kernels. So here's a measurement cost of measuring the latency of all sampled kernels. So this is the cost for NN meter to measure how all those kernels in CPU, GPU, and VPU is individually. There are 2.5, 1 day, and 4.4 days, and all those can be done on new devices. So if you have today you have a new device, and you only need to take for less than a week to make all those good prediction on latency, and which will benefit your future design for DNN models. So these are the results, and right now I will be talking about the conclusion. The first one is that NN meter is an efficient system based on kernel level prediction. So as opposed to operator or model, this is the kernel level prediction. Second, NN meter can capture the runtime asset optimization that reduces the latency. How to reduce it? We have better predictions. And third, NN meter can handle on-scene model graphs. Unlike to others, they have a pretty consistent accuracy and in terms of all the new models that are introduced. Then NN meter has a large accuracy to previous methods, and this is all already said in the results section. And then kernel detection and adaptive data sampling. These two techniques, they solve the problems of the challenge for kernel finding and the cost reduction of the NN meter.
So that's it?
Yeah, and that is it. And if are there any questions?
Let's thank our speaker first. And any question? I'm gonna stop recording here. we can talk about the question offline.